So if we have a function, y equals f of x, and I've got just one that's in general, kind of function here, curve. We talked about drawing a tangent line to that, and explored different things about it, but what we want to look at today is how can we join the tangent line discussion with the limits. And it turns out there's a couple ways that we can do that, a couple of formulas that allow us to find the slope of the tangent line via a limit. So let's just pick a point here, call it A, x for x, the x value A, and we'll just draw in the tangent line here. How did we come up with that slope of that tangent line at A previously? Well, the way we did it previously was we said, well, let's look at the secant line slopes, and then draw in that closer and closer to it. So we came out here, I'm going to kind of exaggerate the secant line, because we probably wouldn't go out that far from it. We usually just kind of go a little bit. But if we could come up with the slope of that secant line, which we can because just using the slope formula, okay, and so we call that our variable x point. And so the secant line slope is just the difference of the y's over the difference of the x's. So this point is a f of a, and then this point would be x comma just f of x. You know, we pick out whatever values we want. The a is fixed in, a is 1 or whatever it is. But then we vary x, we kind of draw it in closer and closer to the a, right? Remember doing this a section or two ago. All right, so the formula, the slope formula here then would be difference of the y's, f of x minus f of a, over x minus a. Now that gives me this secant line slope. And remember what we did then is we called that point Q and that point P, but we drew the point Q in closer and closer and closer to, right, we did it with the table, like we did the XQ values, then we did the MPQ table, and we got these X values closer and closer into the A, so X went to A. Yeah, so this, we didn't call it that, but now we know what we call that is this process right here using this table, it's the limit process. And so we found out that these values, whatever they were, was the limit as this X value, the X of the Q value, went to A. Excuse me, so that's how we get this slope of the tangent line. We take these secant line slopes and apply a limit to it. And here's what it is, okay? So to find the slope of the tangent line, call it M, it's the limit, M equals the limit as X approaches A. So I'm going to pull these X values closer and closer into A, right? So these X values, I'm going to say that's 1, so I do 1.1, 1.01. And matter of fact, I could think about it going the other way. If we did that in that section, we went the other way too. So it's the limit as X approaches A of our secant line slope. And we're going to put it in this form because now we know some stuff about how to evaluate these limits without using a table. We no longer are going to have to rely on a table to do this because, yeah, we just plug in the various pieces And we should be able to figure out that limit using those techniques, factoring, conjugate method, those methods. Okay? This, because like I said, we're going to get another formula here in just a second. This one they'll refer to as definition 1. So this is the slope of the tangent using definition 1. And the other one we'll call something different, but if it refers to definition 1, that's the formula that we're going to use. M equals the slope of the tangent for M. X approaches A of this lovely little limit here. Okay. So let's just use definition 1 to find the slope of the tangent. Use definition 1 to find the slope of the tangent for y equals x squared at the point 39. Okay? Use definition 1 to find the slope of the tangent for y equals x squared at the point 39. Okay? Well, it's really just plugging in some values here. Now, the first matter here is we need to figure out what A is. A is, back to my graph here, the A is the x value I want the tangent at. That's what A is in this formula. So what's the A? What's that A value here? What's the x value I want the tangent at? So this is A in the formula, okay? It's an x value, but as far as the formula goes, the way we're doing it here, A is the x value of the point, okay? So its limit as x approaches 3, because that's A. And let's just write this formula with just changing the A over. So the f of x minus f of 3 divided by x minus 3, just to kind of get going here. Okay? All right. So to compute this limit, I need to replace what f of x and what f of 3, what those are in my formula there. Okay? So that would be our next step. F of x, well, f of x is just the y value evaluated at x, and so y is equal to x squared, so y is f of x, so the f of x is x squared. And then of course f of 3 would then be the y value at 3, so 3 squared, so that'd be 9. So f of 3 would be 9. Yeah, this is, I mean, they call it, they may call it f of x, they may call it y, they may call it some other value, but it's just the function value that we're dealing with there. Is that okay? And then x minus 3 over x minus 3. Okay, so this is what I'm saying. Now that we know a little bit about what we know how to evaluate that instead of relying upon a table, because tables can be misleading. Plus, it's actually a little more work than we have to do here, because how can we evaluate that? Just by factoring, can't we? Even though if we plug it in right now, it goes 0 over 0, if I do a little factoring, this is going to work out so nicely. That's why we did all that work with limits. We're doing it. Yeah, this factors, the top factors, x minus 3, x plus 3, and that goes nicely with the denominator, because the denominator then cancels with one of the factors. And now what can I do? Substitute in, can't I? Now x goes to 3, so I can do my 3 plus 3. This is going to be 6. All right. Okay. Now, let's go ahead and excuse me. Let's go ahead and do this. No. Let's go ahead and, because there's one other thing I wanted to make a note of here for us. So what would be the equation of my tangent line at 3, 9? Well, that's where we use y equals mx plus b, or that's where I choose to go anyway. Because I now know the slope of the tangent line at 3, 9 is 6. So we've got y equals 6x plus b. And then we can plug in our xy, which is 3, 9. Y is 9, and x is 3. And that allows me to find the b. And that would be -9 is b. So we've got y equals 6x minus 9. Okay. So they'll probably have you do that step as well in some of these problems. But the thing I wanted to mention here is let's go ahead and graph our tangent, the function and the tangent line that we found here. So I wanted to make one other big point about this. All right. Yeah, I think it may not be the best one to graph on our calculators here, but it's okay. It'll work. X squared, you know what that looks like, and then 6x minus 9, just a line. And hopefully that, yeah, it's a good one for this point. Okay. Y equals x squared, our function, and then tangent line. Looking pretty good. Here's the next point about all this that we're doing here. True, technically speaking, this tangent, the only point it hits is the 3, 9 point. However, especially with the way ours graphs, or if you do it -10 to 10, x and y way, this, if you look at that, zoom in, or you really have to zoom in here, the graph and the tangent line are pretty much one and the same right here. I mean, technically it's only hitting at 3, 9, but do you see much difference between the graph and the tangent line? I mean, even further out from away from that point? There's not much difference. This line and the curve pretty much are hitting one another for looks like quite a bit of ways, but technically it's only hitting one point. Well, the point of all that is this, what we can say then is the slope is 6. That's the slope of the tangent line. But really what we could consider is the slope of the curve at 3, 9 is 6. Because in a way, the x squared, the parabola, is kind of straightening out, if you will. I mean, it's more curvy down here, but the slope of the curve, so the slope of the tangent line is 6 at 3, 9. what I'm saying is this. Not only can we say the slope of the tangent line is 6 at 3, 9, but the slope of the curve at 3, 9 is 6. That's what I'm trying to get you, make the point of here. So we also can say the slope of the curve, y equals x squared, specifically, is 6 at 3, 9. So the slope of the curve. Sometimes you'll hear that referred to as not necessarily just the slope of the tangent, but the slope of the curve at that point. All right? Now, if I went to another point, like over here, -1, let's call it, would the slope of the curve be 6 there? Well, no, because the tangent line, we have a different slope. It would be a negative slope. So you could really only say the slope of the tangent, the slope of the curve is 6 at that one point, particularly for this one. But at that point, that's the slope of the curve. Now, it's curved all the way around, so there's infinitely many slopes for the parabola there, the x squared parabola. But anyway.